Hi, this is Robert Bolaños. Welcome to Input Filter Inrush Current Design lecture. This is going to be on how to design a inrush current limited circuit. That's one of the problems that you will end up having if you don't have a control circuit. Here you have a typical input filter. It consists of a input section. Now I've simplified this. I'm not showing the Y caps. It's just I'm going to be concentrating on the differential. But going back to my first bullet, the main purpose of the input filter, and we'll look in here, is to attenuate the currents that are generated by your switch mode power supply. So typically you can have these currents very high. Okay, so this could be a flyback. In this case, since you have a little bit of a initial, it means that this would be a CCM flyback, or it could be a forward, or any other topology. So that current is actually flowing in that direction, back and forth, and so forth. And what you want to do is you want to make sure that these caps, basically this inductor, which is the differential, these are two coupled inductors in the differential mode, along with these caps form your differential mode. And what you want is most of the current to go through the caps. Basically, you want to shunt the current. Oh, basically, you want to shunt the current through here, and you want the impedance, the Z impedance, to be high. High. Okay. If you don't have that, then let's say if you don't have a differential inductor here, then the currents will end up going into your bus, V bus, or you can, or V input, and then you're going to pollute, or you're going to corrupt your bus, and then you're going to have any other devices or instruments uh, be compromised. Okay, so like I said, in this, going back to the main bullet, is to attenuate uh, the current. And then I want to add one of the notes that I have here is I have two 43 microfarads here. This should be a 43 microfarad. And then we have a 180 microfarad with a resistor. This is for damping. And typically that will satisfy the Middlebrook criteria. I do have a video on that, so if you're interested on that. And this LC is a low pass filter. It's a second order. And by looking at the equation, C are these capacitors, L is that inductor. And as typically when you increase your capacitance, the resonant frequency of a low pass filter gets lower, but at the same time the inrush current will uh, actually it's supposed to go up. Okay. Why? Because you got more capacitors. Okay. So making the capacitors bigger will lower the resonant frequency, and it will attenuate the current from the SMP. In other words, it's going to limit this current, but you're also going to have current to charge these capacitors up, and I'll explain that. So basically it creates a problem in that if you have too much capacitor, you might trip the input voltage. In other words, if you have a circuit breaker somewhere down the line, or a solid state relay or a current limit, it might sag the voltage. So you're going to see perhaps also a large current spike in your input voltage. So you need to design a slow start, or you can also call it a inrush current circuit. So how do you design that? Okay, well, to do that, we're going to review a little bit of the Miller cap, or the Miller effect, which is one of the effects when there's a capacitance from gate to drain, and we're going to use that to our advantage to design a circuit. Okay, so here is a simulation if you don't have an inrush. So basically this is no inrush current circuit. And this is your input voltage, and this has a slew rate, I believe, of 500 microseconds, or time rise, T rise. And you can see this is the V filter. V filter is right here, and this input is right right there. Okay, now we're measuring the input current right here at the input bus, and if you notice, it's almost 10 amps. And mind you, the steady state current of this is only half an amp, but you end up with 10 amps. So that's a huge voltage spike. Okay, so we're going to review a little bit of the Miller cap, and I'm going to make some assumption. And here I have a MOSFET, and typically there's a internal CGD. We typically also call it the Miller cap, so it's internal, but you can add a external cap, and that's what we're going to do. We're going to use a external cap to create a input inrush current. Okay, so here is the switching characteristics. And this voltage here is your VDS, or VD, which is that point. And when the MOSFET is off, let's say it's off in this transition, and then you apply a voltage, the voltage at VGS from here to here doesn't rise instantly. It takes time and it rises slowly. Okay, and it rises from 0 from the time that you turn it on. This is when you turn on, T on. It rises, and then you'll see that there's this little area where it flattens out, and that's called the Miller plateau. And during this time, your drain will be basically high, and then you start seeing a transition. And it transitions during this time, the Miller plateau. And then once the Miller plateau, and basically during the Miller plateau, that's when you have current flowing through the cap. It's called displacement current. Okay, and once the cap, the Miller cap, is fully charged, then the gate keeps charging until you end up at your steady state. Okay, and typically we will charge steady state to about 12 volts. Okay, 12 volts. So we're going to use this to derive an equation, and we're going to make some assumptions. And the first assumption is we're going to assume that VGS is constant during the Miller cap or the Miller plateau. That means that there's no, during this time, during the Miller time interval, right, there's no current going into the gate. Okay, in other words, most of it is flying, or most of the current is going through the Miller cap. Okay, so that's the first thing. So then we can say that the gate, which is this here, the current through the gate, is VG, basically the voltage at this point at the gate is going to be VG, this input voltage. You know what, let me put this, say Miller gate, and I'll call this VG. Well, I'll just call it VGS for right now. So V gate, so this will be V gate minus VM, and the assumption is that VGS is constant, therefore VGS is Miller, so that's V Miller, divided by RG, which is that RG. So you have this equation. Okay, and then the other equation we can write is, let me erase this a little bit. The other equation is during the charging, this node is going from VDS to basically VGS, so that you have current going through there. So we can write this equation, and we can say that this is the current so this is the current through the Miller, and this is the current, and we can say current through the R gate resistor. So let's put it that way. Okay. Okay, so we have two equations, and then we can make a statement that these two are equal to each other, so that gives this equation. So then we substitute their equivalence. Okay, and then we solve for dt. So now we have a general equation, which is very useful, and we'll show how we'll use this equation. Okay, so now let's assume, if you notice here on my simulation, this is 10 amps, and let's suppose we want to cut it down to about 2 milliamps. So let's say we have a requirement that looks something like this. Let's say that the customer says we don't want the current to go above 2 amps within a span of 20 milliseconds. Okay, so we're going to use that. So we're going to say that 2 amps is our I limit. I limit, okay, which is right here. And D time for right now, let's say your spec calls for 20. See if we can make this smaller. Okay, or at least this is the maximum time that we're allowed, but we're gonna see, we're gonna calculate this actually based on that requirement. You'll see what I mean in a little bit. Okay, so this is how we determine that. This we're looking here, this should be 43. So we got 43 here, and this will be 43 and 180. So I end up with 266 microfarads. And then we use the general equation for a capacitor. Everybody knows this equation, I equals CV, C times dV dt. So we can rename this, say that this is the total, which is this, goes in there. And then the V input is actually this input voltage. And the example I'm using, I'm going to use 28 volts. So what we're going to do is we solve for time. We end up with this equation. Okay, so now this is where we substitute. Our requirement, or I limit, is 2 amps. Okay, so now remember we said that we're going to recalculate this. In other words, we can't be bigger than 20 milliseconds. Okay, so we're going to recalculate that, see what kind of time we would need to limit it to 2 amps. So when you plug in the numbers, plug in the capacitance, the voltage, and your I limit, we end up with a D time of 3.72 milliseconds. Okay, so now we're getting ready. So this is the slow start, or the inrush circuit, and it consists of the 2 resistors. That's a voltage divider, and then this is your C Miller cap. And basically this is the drain, gate, and the source. So there's this cap between the Miller, or the gate, and drain. Okay, And there is another capacitor, and I'll explain how to use that one or how to set that, which is real simple. Okay, so the first thing that we have to do is we want to get it into this format. This format. So we're going to simplify this circuit. Okay, so we take the two resistors and we find the Thevenin. Hang on, let me start again. So we can do this. .28 volts, and we'll find the Thevenin voltage. Basically, what is the voltage between the gate and the source? So in this case, we're going to find the voltage across R1018. So we put that in the denominator, and then we divide by the total, the two resistance. So we end up with a VTH. VTH is what being applied from the gate to the source of 12 volts. Okay, and then we have to find the Thevenin, and the Thevenin would be looking in this direction. Actually, I'm sorry, not that there. It's looking in that direction. Excuse me. And it's basically the parallel combination of R1018 and 1019. So these two. So we end up with 85.7 k ohms. Okay, so this is the general equation that I derived up there. Okay, so now what we're going to do is we're going to solve for GCD, and here's the equation. It's DT VG gate, VM is the Miller, RG, and VD. Okay, so now we substitute where it says VTH or VG, we'll plug that in there, and then RT, we'll plug it in for RG, so you end up with this equation. Okay, so this is the time that we to limit 2 amps. We calculated that we needed a time of 3.72 milliseconds, so that's in there. VM, typically VM is the Miller voltage. It's around 4 volts. If it's not 4 volts, you can measure that and plug it in. And then in my example, I'm using 28 volts. When you plug in these numbers, I end up with approximately a Miller cap of 9.72. So let's go ahead and make that 10 microfarads or nanofarads. Okay. So let's do a simulation. Let's go ahead and simulate the first. Yes. Okay, change this to 43. And just to show how it looks, actually the current is actually even higher. Here's the current, and it's actually 12.98, almost 13 milliamps. 13 milliamps. Okay. So now let's go to our slow start circuit. Okay, this is 43. Here we have the end capacitor. It's 10 nano, and I believe that's what I calculated. 10 nano. Okay. Okay, so let's go ahead and, oh, so here's a capacitor, and right now I'm going to set this to 1/10, so you can see what the uh, what happens with this one, and I'll explain what's happening. Okay, so now you notice I put a 10 amp or a 10 nanofarad, and if you notice, it's 8 amps. It's not doing what it's doing. Okay, so let's see what's happening. Okay, so when the input voltage comes in, you have a resistor here, and you have a resistor here. It's a divider network. Okay, now at t equals 0, this is off. It's 0. So basically, if this is 0, that means that this capacitor, you can assume that it's connected here. So let me show that what I mean. So basically you have two resistors, and I had that 1 microfarad cap, nanofarad cap, this is ground, 28 volts, and this would be 10 nano, and I believe, let's say 150 and 200, 150 and 200. $50K, 200. Okay, so this is 0. It's discharge. It's at 0 volts. So at steady state, these are the dominant at steady state. But when you have initial or a rise time, the caps form a voltage divider. Okay, so basically VGS is right here. This is the source. This would be the drain. So basically VGS, if this is big, much bigger, we'll see most of the voltage. In other words, it's going to try to turn on the transistor or the MOSFET really high. So what you want to do is, the rule of thumb is you make that 10 times bigger your C Miller cap. So in this case, we're going to make it 100 nanofarads. Basically, it's going to do, it's going to divide or make this voltage about 2.8 volts. Basically, it's going to be a tenth of that. Okay, so that's what you want. So let's go ahead and do that change. So this is 10 nano. You make this 100. So now there we have a much better there we have a much better controlled input current. If you notice, now it's in the ballpark. It's 2.2. Okay, and remember we calculated a time of 3.72 milliseconds. Okay, so take the time from there to there. Okay, that's pretty close. Okay, okay, so it's 4.0 milliseconds. So it's pretty close to what I calculated. So now if you want to get this underneath, you can increase your meter cap using Spice just by increasing that voltage or that capacitor. So this is a way you design a inrush input filter. I gave you the procedure that I've used, and I hope you found this design tutorial helpful. If you like the video, please give a thumbs up, subscribe, and share with other young engineers that are learning how to design. Thank you for watching.